Hello and welcome. Back by popular demand, we have the second exam, second practice exam rather, that I'm going to go over for all of you today. It actually is exam 2. The first one, we want you to draw a simple example of each functional group. It has to contain 3 carbons, should be in zigzag format, and no R groups or additional things. So an alkene is a carbon-carbon double bond. So that would be an alkene, and since we need to make it have 3 carbons, this is pretty much the only answer that you can come up with. A carboxylic acid has to have a carbon-oxygen double bond. That carbon has to be bound to an oxygen, which is bound to a hydrogen. And since it needs to have 3 carbons, we go 1, 2, 3. And that's pretty much the only thing that you could come up with for a 3-carbon carboxylic acid. An alcohol has a carbon attached to an oxygen, which is attached to a hydrogen. 1, 2, 3 is one way of doing it. The other possibility would be 1, 2, 3 and make isopropanol. A halohydrin you're familiar with from that reaction in chapter 8. And a halohydrin has a chlorine, it could be a bromine, an iodide, or a fluorine as well on one carbon, and an OH group on the next door carbon. In order to make it have 3 carbons, you just add one more right there. Could have added it to the other side as well. A 3-carbon ketone, only one possibility, acetone. This is where we have carbon on either sides of the carbonyl carbon. And again, in case you missed it, a carbonyl is a general term for having a carbon-oxygen double bond, but it's not a functional group itself. Next, we're going to figure out the degrees of unsaturation in each compound. So 1 degree of unsaturation, if you're looking at a structure, would be 1 ring or a pi bond. So you can see on our example here, we have 1, 2, 3 pi bonds, and then 2 rings. Okay, so once again, that's not that you need to note this, but it is 3 pi bonds and 2 rings. So that's a total of 5 degrees of unsaturation. And this next one, we have 1 ring and 3 pi bonds. So we have a carbon-carbon double bond, another carbon-carbon double bond, and then a carbon-oxygen bond. So that's a total of 4. For these next ones, we have to use our strategy or formula where we remember that we're going to be adding any halogens to make what we call a hydrocarbon equivalent. We're going to subtract, any nitrogens, and we're going to be ignoring any oxygens because they don't affect the degrees of unsaturation. So the hydrocarbon equivalent of this compound, C7, we would have to add the number of halogens, which is 2, to the number of hydrogens. So its hydrocarbon equivalent is C7H12. Its fully saturated form of the formula CnH2n 2n plus 2 is here. It's C7. 7 times 2 is 14 plus 2 is 6. So now we're going to be focusing on this number here, the 16 and the 12. And we see that the difference between them is 4, or 2 pairs of hydrogens. So this molecule has 2 degrees of unsaturation. For the next one, we're going to find our hydrocarbon equivalent. We see it's C5. And we're going to ignore those number of oxygens. We're going to subtract the 1 nitrogen from the number of hydrogens, so it's just going to be a 9 minus 1, so C5H8. And then we look at the fully saturated formula for a C5 compound, which is going to be H12. 5 times 2 plus 2 is 12. And then we are going to compare those 2 values, the 8 and the 12. Once again, we see that there are 4 hydrogens missing from the fully saturated form. And so that works out to be, once again, 2 degrees of unsaturation. So I just took a quick little break to draw in a molecule. If you have a hard time remembering these rules here of when to add, subtract, or ignore the things, you can always just try drawing a compound with the number of degrees of unsaturation you think it has. So this problem that we did, we said, hey, we think there's 2 degrees of unsaturation, so let's draw a molecule with 5 carbons, 1 nitrogen, 2 oxygens, and damn it, I left out an oxygen. Okay, with 2 degrees of unsaturation, and even if I added in this other oxygen, it wouldn't matter. Okay, so I still have 2 degrees of unsaturation, 1 ring and 1 double bond. There's those 2 oxygens, 1 nitrogen, and you can see that I still have 9 hydrogens, so I know that I did this correctly. Next, we're gonna figure out, or just give a quick identification of whether these compounds act as nucleophiles or electrophiles. You may remember an example of a base being sodium hydroxide, and the thing that sodium hydroxide does is it picks up protons, but more importantly, we want to figure out whether they are electron-rich nucleophiles or electron-poor electrophiles. We can see that the arrows started at the base. This is where it's electron-rich because of oxygen's lone pair. This is a nucleophile. We saw several examples in class where an alkene was electron-rich and donated its electrons, in this case to the hydrogen of hydrobromic acid. So we see that the alkene is also a nucleophile. In the example earlier, we saw here that this acid, the thing with the proton, was accepting electrons, so it must have been electron deficient, or an E for electrophile. And then the last example down here, we want to figure out what's the most and the least stable carbocation. Things we want to remember is that alkyl groups inductively donate, and that's going to be good for a positive charge, because it's kind of neutralizing it, whereas electronegative atoms or groups withdraw those electrons. So here, this first one, we have a methyl carbocation. It has no alkyl groups. So we're just going to make that little note. R for alkyl groups, right? So we'll define that, R groups. This is a tertiary carbocation. It has 3 R groups. This next one has no R groups, but it has 3 electronegative atoms, which are withdrawing electrons from that positive charge, and withdrawing in this case is bad because we have a positive charge which is deficient of electrons, and if we're trying to pull more electrons away, that's just not realistic. Moving on for classification, this is a primary carbocation. This carbon is only connected to 1 carbon, so it's primary. This one here is a secondary carbocation because it's connected directly to 2 carbons. So from that, we should have enough information to rank. The most highly substituted is the tertiary carbocation, so that's going to be the most stable. Next is the secondary carbocation. We then have a primary carbocation, which is not particularly stable on its own, but it's better off than that CH3 or the CF3 group. And then, as we already said, having those 3 electronegative atoms withdrawing electron density from something that's already electron poor is very bad for business, very bad for stability. So this is going to be the least stable, and then the methyl cation is second to last. That is page 1. See you at page 2.